very much to get home before it gets dark. I used to ride in New York City a little bit, and I rode a little bit at night, and it was very dangerous.
Because at night usually people are driving very fast.
Well,
Because there are
the
very few cars, so
the other problem at night is you can't see problems in the road, and I had an accident at night. Good morning. I don't think this has what you were looking for, but it was the one that came yesterday.
Right, thanks very much.
So I think it's the wrong one. Hi?
No, it's the right one.
If you still have a question on the probability, you should talk to me afterwards, I think, or some other time.
I went with one answer because I got it 3 times 3 different ways, but I have 4 answers.
Right. Well, you did the probability density function. I don't know if we're talking about the same thing. It does it good. You were asking about how to get one of the probability things. Which one were you? For the Gaussian, yeah. Okay. Because you got that correctly. I looked over the homework you did by doing the PDFs, so that's fine. Okay. Why don't you? Have we started? Okay. We've started. What I'm going to do today is go over the homework from last time, and then we'll get on to something that we haven't done before, because it would be silly if we did what we've done before. So what I'm going to do is, first of all, go over the series of statistical tests that we had before. And the first one was we had this data that you fit by Gaussian by determining the mean and the variance. And then the next question is that Gaussian really a good fit to the data? So what we're going to do now is to see how to do the chi-square test to see whether it was really a good fit to the data or not. So this is homework number 3. Thanks. Homework number 3. And there's a attendance sheet being passed around, and I have new homeworks. So I have 1, 2, 3, 4 homeworks. 1, 2, 3, 4. Here, why don't you pass those around? Thanks. And shows I can count to at least 4. Where the deal of the chi-square test, the basic principle, is that we evaluate, we have a nice red graph here of frequency or number, let's say, of certain values. So we have a distribution, so we're dealing with a probability density function. And this is an important point, that we're not fitting like a straight line to data, we're fitting a distribution. So that's very important here. So this is fitting a distribution, not like a line, for example, of y versus x. And we have some values and these are values from the experiment. And what we're trying to see is if some distribution also fits the data, and we can determine the values that would be present from the distribution. So this is going to be the predicted. So we have to know how we're doing this prediction, and we assume we know that. And we're trying to compare the experiment to the predicted. And the value of chi-square, again, this is the Greek letter chi squared, is equal to the sum of the experimental values, which I'll call E, minus the predicted values, which I'll call P, squared divided by the predicted values. And these are the predicted values within bins. Somehow when I say that, I can picture these garbage bins and the truck making all the noise, picking them up, putting it in the back of the truck. But if I was better at making paper airplanes, I would do that, but I'm not. And this is the value of chi-square. So what we do is we determine the value of chi-square and the number of degrees of freedom. So nu equals the degrees of freedom is typically equal to the number of bins minus the number of parameters that are needed to define the distribution, which in this case is going to be 3. Because we have the total number of events, we have the mean and the variance if we're looking at a Gaussian. So what we need to do is, first of all, in order to use this, is determine the expected values, which you did in the first homework. So I'm going to put here, this is very tricky today. And in the first homework, for example, we could do this. So we have data, and we're trying to see, is this data really Gaussian? So there's that Gauss again, whose name has appeared today and on Wednesday, and although not yesterday. So he escaped one day. And we could do the comparison either by using the histogram, where we integrated the probability density function to determine the number predicted within each bin. So we could use either the data from the histogram, or we could use the data from the probability density function. So we had both the data and the predicted values. And those numbers for the, and I'll use this one just because it's equivalent. In fact, if you think of, oh, I'm not going to say that. But I almost said it, but I wasn't sure it was true. This is a spreadsheet which shows some of the predicted values. These were the centers of the bins that I had. This is the amount of data in each of those bins. Anyway, it's bigger. This is the probability density function computed from the bins. This is the probability density function computed from the Gaussian. And this is the predicted number in each bin. And then this is the chi-square value for each of those. And the sum of all of that is 12.5 roughly. So the answer is that in fitting this data to the Gaussian, the value of chi-squared equals 12.51. And the number of degrees of freedom, in this case I had 10 bins. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So remember, this is the number of bins, not the total number of data points, minus 3 equals 7. So now I need to calculate what probability corresponds to this chi-square. And there are a couple of different ways you can do calculations like this. And I've been trying to mention this all along because you need to know actually how to convert this to something real. In this case, the way I did this is there are programs in the book Numerical Recipes by Press, Tucholsky, Verdeling, and Flannery. And in this book, I had actually programmed these. The most popular version of this, of course, is in C, but of course I programmed these probably in BASIC, and which don't run anymore on my machine. Actually, at a different point, I also programmed them in Pascal. But and what these programs do is given a value of chi-square and nu, they allow you to compute what the probability is. But there are other ways to do this too. The other book that I've been mentioning a number of times, which is by Abramowitz and Stigund. Which is called the Handbook of Mathematical Functions, also has tables of these things. And if we're real lucky today, when I pick up my copy of Spiegel here, on the table, it should have in the appendix in the back a table of chi-squares, which is actually here. So let's see if we can look up from this table. We have 7 degrees of freedom, and that's along this line. And we have about 12 something. And so if we look up here at the top of the column, this says that the chi-square probability of that is 0.9. Focus. 0.9 over here. So that's the cumulative probability. So the tail of this distribution is 0.1. So therefore, if none of these other methods worked for you, we found that given chi-square of about 12.5, it had 12 in the table, and nu equals 7, the probability of getting that by chance is about 0.01. Now, in my more exact calculation, I found that given chi-square of 12.51 and nu equals 7, that the probability that this is due to chance is actually 0.85. So this is a little more accurate calculation. But the basic point here is that this is the null hypothesis that our distribution is Gaussian, is not different than Gaussian, which is the test that we're doing here. And since the probability at the alpha level would be 0.05 that we reject the null hypothesis, we do not reject the null hypothesis. That is, the null hypothesis is true, and so it is not different than Gaussian, and so it is Gaussian. So our data can be represented by a Gaussian distribution. So that's the conclusion from this. Would we have gotten a different result here if we would have used the bins and the estimated predicted values from the numbers within each bin? Instead of the probability density function?
I think so. You use the probability density function?
In this case, we used the probability density function, and we compared the expected from the calculated. Thanks.
If you use the numbers in advance and then calculate the numbers based on the computed probability or computed Gaussian, then essentially what you're going to be doing is dividing your expectant and observed by just some value or multiplying it by some value k or whatever. And then when you, on the top, it's going to get squared, and the bottom, it's not going to get squared. So you're going to end up with an extra factor of k in the outside, which is going to be multiplied by your the value you got for the probability density function.
What I think will happen, the one aspect of that argument leaves out is the fact that we're doing the integral in the other case. I have a feeling, though I haven't done it, that it will work out roughly the same. And because we're integrating the probability density function, so the expected and both change by this sort of odd scale factor, which is not just the total number of events, which would be true if it was just the probabilities. But we had this probability density function. So when we do the integral, we get another factor that comes in. Now, the integral is not exactly the same thing. There are inaccuracies in doing the integral because we've taken the derivative before. So that is, we're looking at the derivative of the integrated form here. And when we do that, there are going to be some inaccuracies in that. But I think we should really get the same result, actually. But I haven't done it. You could do it if you want. I also wanted to mention to you that I got slightly different answers for the Hodgson-Lehmann estimate on one of the two curves that you did.
Yeah.
Not large.
It's possible for the one when the numbers when the values were the same and say the x direction, or there was one I think maybe like the height or the weight, there were values that were the same. for sake of simplicity, I just called that, well, I couldn't divide by 0, so I called that slope something very high, and that affected my median point.
Okay, I don't remember how I handled that. That's an issue that comes up. So I may have ignored those, and that would make a difference in the median. And also, the value of r that you had was really r squared. So you had 0.75, which was actually r squared. Sorry to, so that's an aside. Okay, so that's the end of the first part of the homework. Did anyone have any questions on that? Okay. So let's do the next problem on the homework, which is problem 10.9. And it exists here. I won't be able to enlarge this enough to read it, but I will read it. In problem 10.9 was, let's make sure it was 10.9. 10.9, okay. The breaking strengths of cables produced by a manufacturer have a mean of 1,800 pounds and a standard deviation of 100 pounds. So let me maybe write down here the numbers as I read the problem. So this is problem 1019. The breaking strengths of a cable have a mean of 1,800 pounds and a standard deviation of 100 pounds. By a new technique in the manufacturing process, it is claimed that the breaking strength can be increased. To test this claim, a sample of 50 cables is tested. So we're going to test 50 cables, and it is found that the mean breaking strength is 1,850 pounds. Can we support the claim that this is better at the point 0.1 significance level? So the hypothesis here is that the new cables are better than the old cables. That is, the mean of the new cables is greater than the mean of the old cables before. So first of all, is this going to be a one-tailed test or a two-tailed test? Say it? One-tailed. Why is this one-tailed?
Because you have mean and the standard deviation for the population. You want to compare if that sample belongs to the population or not.
Right, but the crucial point is that what we're trying to find out is only if it's better, not if it's different. If it was worse, this is better. And this end of the tail would be worse. I guess worse has 2 exclamation points. And we're not asking the question if it's different. So this would be the distribution, and this is the values. So this might be the distribution, the old distribution. We're asking if the new values are here. We don't want a two-tail. We don't want to add these probabilities because we're not asking whether it's different. We're asking only if it's better. So this makes it one-tailed. The other thing here is that we're given this initial mean and standard deviation. So there's no error in that. We know exactly what it is. And that's a crucial point in how we handle this. So the null hypothesis here is that the 1,800, the old value, is really the same as the new value, or that the difference between them is due to chance. And we're going to test whether this null hypothesis is true or not. And a good way to do this will be to use the z-score, which we've used a number of times before. So z will be equal to the old mean 1,800, or let's say 1,850 minus 1,800 divided by the standard deviation. Let me write it in symbolic terms first. Z, we said, is equal to 1 mean minus the second mean divided by s, the standard deviation, over the square root of the number of measurements. Now, we absolutely, this is the mean that we're trying to test, 1,850 minus 1,800. We're told that the standard deviation is 100, and we're going to have 10 measurements. Divide that by 50. Thank you. Now, one of the issues that comes up here is why we're using 50 and not 49. Does anyone know why we're using 50 here instead of 49? Well, we're told that this is the standard deviation. It's not something we got from data. They just told us. So when we know what we're doing, we divide by the square root of n to get the SEM. If we didn't know what we were doing, we'd probably divide by n minus 1. So that's probably why we have 50 here. Okay. In any event, this number works out to 3.55. And we can now calculate the probability that this z-score for a Gaussian is greater than 3.55. And this value, I don't know where I have the first one here, but I've calculated it in a number of different ways. From the tables from Spiegel, I got that this p-value was 0.0002. And let's see which table I got that from. Probably from this table. So I've got to go all the way to the bottom of this table. And this is 3.5 something, and this is 0.998, so that means the remainder, the last part of the tail, because what we're doing here is from the center, so this is a half, and the center out to here, and we want that little remaining piece. This whole block here to the right of 0 is a half, so anything that's, if I subtract a half from what I find here, that will give me what's in one tail, and 3.5 here gives me 0.4998, so the remainder is 0.002. So from Spiegel, I get 0.002. I'm going through this because I think in actually handling real data, you have to make these calculations. I want to give you a number of different mechanisms on actually how really to do this. So from Spiegel, from looking up in the book, we've got 0.002. From I have 3 zeros. Yeah, I think that's correct, actually. Oh, no, it's just, no. So it's the problem is with my mouth, not with the book. I don't need to show the book again. Right, it's 3 zeros. Thank you. If I look at the tables of Abramowitz and Stiggon in the Handbook of Mathematical Functions, the value from the tables there were 0.001926156. They have more decimal places. And the value that I calculated from my basic program, it was 0.0001927. So these are the different values. So what's the answer here? Is this really different? Is the new method really producing better cables? This is a yes-no question. Yes, right. So the answer is yes, the cables, new cables, are better. And if these were elevator cables, what's the jargon word? We wouldn't call them cables. What would we call them? We call them wires. Okay. Now, just for fun, this was using the Z statistic. Just for fun here, because I have fun all the time, I calculated, although not this year, apparently this was calculated last year, I only had fun last year. I also did a t-test on this data to see what the difference between the t-score and the z-score would be. So the t-statistic now is equal to 1850 minus 1800 over 100 by the square root of 50. It looks pretty similar, actually. So it's 3.55. And now I need the number of degrees of freedom. Now, typically, this would be, for each constraint I have on the system, I lose 1 degree of freedom. The only constraint I have is the total number of the measurements. So this is sort of an unusual situation. So I did 49 for the number of degrees of freedom. And then what I did was look up in the table how the 49 degrees of freedom differs from the infinite number of degrees of freedom in the z statistic. And the answer is it doesn't differ at all. The difference was too small to tell. So let's see if I can find the t statistic in here. And it's hard. I'm not exactly sure what I did on this. Okay. So in this case, the t statistic, because we have so many things, is really exactly the same as the z statistic. So I couldn't tell any difference. And this shows that when the number in the data set gets very large, that the t statistic and the z statistic are the same. So that's the only point that comes out of this. Now there's a slightly different way of answering the question, because the question we're asking is, for the null hypothesis, is the probability less than 0.01? So one of the things we could have done here is calculate when the probability is equal to this, and then see what the value of z is, and see if our z is greater than that critical z, or our z is less than that critical z. And that's another way of handling these statistical tests if the tables aren't available. So when I did that, I found that the probability equals 0.49 for one-tailed distribution when z equals 2.33. And I probably did that from the table here. So what I did is I went through this table to see about when I could find 0.49, which is about here, and it's somewhere between 2.3 and 2.4. 2.3 and 2.4 means that the remainder for a one-tailed test would be 0.01. In fact, when I calculated it more accurately in a way that my notes don't explain, I found that actually that z was 2.33. And I don't know how I did this. In the old days, I actually really did interpolation on tables. I could have done that. I don't know whether this came out of a program. I have a program, of course, in BASIC that does this, or used to do this. But now the z that we got, actually, if you remember from the previous page, was equal to 3.55. So this is the critical one for the test, and this is ours. And since ours is greater than this means it's statistically significant. The variance or the deviation from the mean is larger than what we need to sustain the 0.01. And this is another way of handling data in tables sometimes. If it's hard to get the value you want, if we're looking at a certain level, we can look up the value for that level and then use that. I lost a pen, but I found it. Okay, so that's the end of this problem where we've seen a number of different ways to do that. Are there any questions on this problem? This is going to be slow and boring, but I'm going to go through all of these in all these different ways, because if you don't know how to do them, then you can't do them. And I think it's really worth understanding how to do these. So the next one is problem 1018, which is here. So let's do 1018. In 1018, the mean height of 50 male students, so n equals 50 of these things, showed above average participation in college athletics, and their mean height was 68.2 inches. By the way, since the Olympics is on, actually I spent about an hour last week in Israel watching, it's my only free hour, watching the Olympics. And I got to watch my sport in the Winter Olympics, which is curling, which I don't know if it made it on American TV. It was on CNN International.
What is it used for?
I just like it. I like curling. It's sort of like bocce and a bunch of other games where you have, it's very similar. A number of games. Scully is similar to that, which is a street game played in New York City. A number of other games which have similar aspects. It has some aspects that are similar to croquet in a way, and in some of the strategy, and I just like that. I still don't understand why they have to be different male and female curling teams. That sort of eludes me, but okay. So back to the problem about athletics here. So we have the mean is 68.2 inches with a standard deviation of 2.5 inches. And then we have another 50 students who showed no interest in such participations. This is probably my group. 67, because they probably don't consider curling a sport anyhow, 67.5 inches with a standard deviation of 2.8 inches. And the deal is, test the hypothesis that the male students who participate in athletics are taller than the others. So is this going to be then a one-tail test or a two-tail test? One, because we're only looking for one direction. Okay. And let me run through the calculation. So the first thing we need to do is the way I would do this. So if I saw this data in an article, what I would do is make an estimate in my head. And let me again run through that to show you how you could do that so you can tell what the answer is. Remember, the combined standard error of the mean is kind of the square roots of the standard errors of the mean, sums of them squared. The standard error of the mean is going to be something like the standard deviation divided by the square root of the number of these things. And so if I do this, if I divide each of these by 50, it's like dividing them by 100 and multiplying by 2. So it's going to be about 0.4 or 0.3. It actually works out to be 0.35 and 0.396. And if I do the sums of this squared, I get a number that the combined SEM is about 0.53. But in my head, I could still estimate this as probably about a half. Now, the difference between these two, we can see, is about 0.7. So if I divide 0.7 by about 0.5, I get about 1.3. And I know that a difference of 1.3 is a probability value of about 0.1. So I would be able to tell, just by playing around with these numbers in my mind a little bit, that this is not going to be statistically significant. It's not going to be meaningless, but not statistically significant. And this is what I would do in my head or with a hand calculator if I wanted to get a rough estimate of the probabilities. So it's very good to have a sense of, given the z-score, what the one and two-tail probabilities are. And I gave tables of this last time. And one standard deviation, one-tailed, is about 30%, a p of 0.3, and 2 is about, I think, 0.05, and this is in between 1 and 2, so this is 0.3. So it's in between 1 and 2, so 1.3 I know corresponds to a probability about 0.1. So I could tell almost by looking at this data without doing the test that this is going to be borderline but not statistically significant. So again, this is the way to make a rough estimate if you're reading data and they haven't given you the statistical test. So as I said, it's easy to have a table if you use often enough of the z-score and the p associated with it, and then to estimate these standard errors of the mean, and you can do it this way. Now I'll do this in a more formal way by using the t-test. So in doing the t-test, the exact combination of the that we need, this z is S1 is S1 squared over N1 plus S2 squared over N2. Okay. No, we're not doing it. We're doing what I did first, I'm sorry, is a z-test to just make a crude estimate also. So now what I'm going to do is an exact version of the hand-waving calculation I just showed you before. And we know that the real sigma is going to be S1 squared over N plus S2 squared over N2 square root, which in this case works out to 0.5308, and when I do the difference between the means, M1 minus M2, over this, then I get 1.3186, and the p-value that z is greater than this equals 0.094 using the one-tailed test. So this is the probability using the z-test, and in this case, the values I calculated from all three sources, which was Abramowitz and Stigall and Spiegel, and my program are all about the same. 1.32 for all of those for the z corresponds to 0.934. Okay, so this is doing the z-test. But now what we'd really like to do is do the t-test on this thing, because we don't have an infinite number. So let's go through the calculation of the t-test on this. And for the t-test, we need to calculate sigma of 1 over n1 plus 1 over n2, which is 1 over 50 plus 1 over 50, which is sigma over 5, if we add that together. And then we need to compute this sigma is equal to n1 s1 squared plus n2 s2 squared over n1 plus n2 minus 2. And we put those numbers in, I get 2.68. And then the t value is the difference, 0.7, divided by this sigma over 5. And that worked out to 1.3 with 98 degrees of freedom. And when I did this, I got a p-value of just about 0.1. So let's compare the p-values. The z-test p-value was about 0.09, and from the t-test, the p-value is a little bit closer to 1.0. And the reason why I'm doing this, although these aren't markedly different, typically what happens here, the z-test the data looks more statistically significant. Looks more significant when we use the wrong test. Okay? So this is typically the reason why the t-test was developed, because when we don't have an infinite amount of data, we overestimate the statistical significance. Okay? So this is, let me write that down. When n doesn't go to infinity, we don't have an infinite numbers, the wrong test, which assumes that n is infinite, that is the z-test, overestimates statistical significance. We'll see this more later, but we can see it here now.
How close does it have to be to infinity to be relatively okay?
Can't spell significance today. These tests, the t-test and the non-parametric tests we're going to discuss later today, unless I continue to talk slower and slower and don't get to them, I would say when you deal with small data sets in the range of, let's say, 10 numbers or 15 numbers, then things become significant. We're going to see today that, because here we're still at 50, we should see today that a typical difference, not always, a typical difference between a non-parametric test and a parametric test, if we have 10 data points, roughly, will be a factor of 2 in the probability. So one test may give us 0.1, and the other test will give 0.05. And that's sort of a typical difference. And the test that's more correct will give us, well, we'll see in the non-parametric case that when we use the right test, we get stronger statistical significance. Just the opposite of what we have here. But in this case, the z-test looks stronger and is inaccurate. Okay? And are there any questions on this problem? Any other questions on this problem? These are all pretty straightforward, and they're also worked out in the book, too. But I just, I think it's different actually seeing it in the book and actually writing it out by yourself. So let's do now 11.6, which used to be here. Here it is. In problem 11.6, in the past, the machine has produced washers having a thickness of 0.05 inches. To determine whether the machine is proper working order, a sample of 10 washers is chosen for which the mean thickness was 0.053, and the standard deviation was 0, 0, 3. Test the hypothesis the machine is in working order at the probability levels of 0.05 and 0.1. So we're back here to the t-test again, and the t-statistic is going to be the mean that we measure minus, let me call this mu, because this is some mean known mystically, so we know its exact value. So it's going to be the difference between our mean and that divided by s divided by n minus 1, which is the t-test when we're comparing data to a known mean. And when we compare it to a known mean, then the number of degrees of freedom is n minus 1. So this t-statistic works out between 0, 0, 0, 3 over 0, 0, 3 divided by the square root of 9, and that's equal to 3 for nu equals 9. And if we look this up in Spiegel's table, okay, so let's see, let's literally zoom in on this. So we have 9 degrees of freedom, and we're looking for a number that's about 3, which is about here. And it turns out this is going to be, from the way I estimated things and calculated them from my own other program, it turns out that the p-value was, whoops, 0.0075. Now, this is a one-tailed or a two-tailed test? Two-tailed. So we have to multiply this p-value times 2. So the p-value is actually then 0.015, because this is the probability that it was either greater or less, and we want that is one or the other. And we want the probability that is just one, and this we want the probability that it's both, so that's twice the p-value. So we can also look the p-values. So we're in between we're in between these two levels. So we would reject h naught at the 0.5 level, and we would accept h naught at the 0.1 level. So here, depending on what level we think is statistically significant, we get two different results. And the values of the t-statistic that correspond to the 0.05 level is 2.26 from the tables and 3.25 for the 0.01 level. And the value we have here is 3, so it's again in between these two values. So again, we can work it both ways. We can, from the p-value, determine the t-statistic and then see what our t-statistic is and compare it. Or we can start with the t-statistic and determine the probability. Now, just for fun, I also did the z-statistic on this, which I'll show you. And the z-statistic now for the same data is 0.003 divided by 0.003 over the square root of 10, and that's 3.16. And the probability that z is greater than that is 0.008. So again, and even if we double this to get the two-tailed, we again see that the z-statistic looks more significant. Even though it's the wrong test to use, especially when n is low, n is 10. So I think we have to multiply this by 2, so this would be 0.016, but that compares to the probability that we got of 0.15. So here it's almost a factor of 10 in difference between the probabilities. And this is why student developed this t-test, because when the numbers are small, we get big deviations between the t and z statistics. Okay. Should I ask if there are any questions on this? No one will ask any questions, so I could ask if there are any questions on this one. Okay. And the last one in this series was 11.8. 1018, 10, 11, 8, which I can't find in my notes, so I can look up here. And in 11.8, we have IQs. Is that right? Oh, here it is. No. We have IQs of 16 students from one area in the city showed a mean of 107 and a standard deviation of 10. And IQs of 14 students from a different area of the city showed a mean of 112 and a standard deviation of 8. And we're asking, is there a statistical significant difference in these IQs at the 0.01 and 0.05 levels? First of all, this is there's something odd about this because by definition there's a fixed value for the standard deviation of IQs, which I forget what it is. Is it 15 or 20? But actually IQs are set up on a scale to have a fixed standard error, standard deviation, which I don't remember what it is. The average is 100. Right. It's those zeros make it easy to pick those things, right? So it's, okay. Well, first of all, is this going to be a one-tailed or a two-tailed test? Two-tailed, right, because we're asking whether they're different, not whether these are, what? Two. Just, yeah, this is just, it's getting worse and worse today. Because we're not asking whether these people are so much smarter or more absolutely fabulous than these people, but we're asking whether there's just one is different than the other. So if we, again, running through the calculation of t, we start off by multiplying sigma times 1 over n1 plus 1 over n2 square root, and sigma itself is equal to n1 s1 squared plus n2 s2 squared divided by n1 plus n2 minus 2 square root, and that works out to 9.44, and the value I got for t was 1.44, and then the number of degrees of freedom is 16 plus 14 minus 2, which is 30 minus 2, which is 28. And I got a probability of 0.150 for this. That is that's the two-tailed. The one-tailed probabilities that I looked up, found out from the table, were 0.075. And so I doubled that. And so this is not significant at either level. Now again, doing this problem the other way, I find that at the p.05 level for 28 degrees of freedom, that 975 on the table corresponded to t equals 2.05. And at the 0.05 level for 28 degrees of freedom with a probability of 975, that t 995, sorry, to get 0.005. So when I double it, I get 0.01. The t-value is 2.76. And the t-values we have here are 1.44, which is less than these two. So again, doing it backwards to test against those levels, I find that it's not significant, and so they're not any difference. People used to do it more this way when it was harder to compute the p-values and you had to look it up in tables. So this goes back to a different tradition. And as I said before, I also calculated the z-value of this. And the z-value was z equals 5 over 10 squared over 16 plus 8 squared over 14. And that worked out to 1.5. And that worked out to the probability that it's greater than 1.5 of 0.668, or the two-tailed probability was 0.13. So again, the probabilities we got from the t-test, the probability was 0.15. The probability we get from the z-test is 0.13, which is what we've seen before in the other test, that the z-test a little bit overemphasized the statistical significance of this. So that's the end of that part. Are there any questions on this homework at all? I think this is pretty straightforward, and it's described in the book too. If people have additional questions, they can just get in touch with me, and I'll go over them. What I'd like to do now is an entirely different set of tests. So far, we've done the tests so far are known by the jargon word of parametric, because the distributions that are used in these tests are characterized, or the values of the distributions are determined by parameters, and the ones we've seen for the Gaussian are actually the mean and the standard deviation. But these tests make certain assumptions that the data really has this form, namely that the data really is Gaussian. So these tests have assumed that the data is Gaussian. And this is both the z and the t statistic. So we'd like to relax that assumption, so we're getting more general. As we start in this course, we're going to get to more and more general things. So we started with Gaussian assumptions. We'll do non-Gaussian, and then couldn't even be considered non-Gaussian. So we're going to get up to more and more general assumptions. So the test we're going to do today is going to assume that not assume that the data is Gaussian. So these are more general tests. Now, these tests still make assumptions. And the crucial assumption, which is my hiding blue pen, that I think they make, although I'm not sure, I think these tests still assume certain properties that I'll call asymptotically Gaussian. And that is that if we had enough data, which we don't, then it would approach a Gaussian. So there are some hidden assumptions in these tests, and we'll see when we get to fractals that these tests are not valid for the fractals. And one of the assumptions here is that the standard deviation is finite. I'm not absolutely sure, but I think these are making these assumptions. And this assumption leads to something called the central limit theorem. And this is an L, not that you can remember the abbreviation anyhow. But we're assuming certain aspects, I think, in these tests of the central limit theorem. We'll see there are more general tests than the one we're going to describe. But these tests are still better than the Gaussian tests. And what do I mean by better? Better. Remember, we're assuming that the data has certain properties. In this case, that the data really is Gaussian. When the data does not have those properties, okay, what it means is that the p-value is not correct that we calculate from this test. Okay, that's what I mean by better. So when the data doesn't match the assumptions of the tests, the probability values that we calculate are not accurate. And that's sort of an odd thing to say, right? Because you punch it into the machine, the p-value comes back, and everything is supposed to be okay. But the real point here is that when the mathematical form of the data doesn't match the mathematical form of the tests, then the assumptions and the derivation are invalid. And so that means that the p-value is wrong. And we're going to see, as we've already seen, the two different tests I showed you before produce slightly different p-values. And as I said, we'll see that sometimes we can get an error in the p-value between what I'll call these non-parametric tests and the parametric tests. When n is small, let's say about 10, the error in the p-value can be a factor of 2. So if you think that's significant, that's significant. I'm not all into these statistical tests, so that doesn't bother me so much. But you know, if you think there's a big difference between getting 0.03 and getting 0.06 and thinking you believed in an experiment or not, then you can easily get those differences for small numbers between the non-parametric and parametric tests. Okay. So the first test I'll discuss with you, which is on the homework, and if you haven't picked it up during the break, please sign the attendance sheet and pick up the new homework. The first test is called a binomial test. In the binomial test, we have something that we compare to something else. And we can use the binomial distribution to see what result we got. So for example, and I'm actually currently arguing with a reviewer about an article about the use of this test. And I think the reviewer is right, and I'm actually wrong on this, but we're still trying to figure this out actually. Let's say I did an experiment 16 times. And let's say I had a control and an experimental condition. Let me actually write control and experiment. So let's say every time I did this, the experimental value was higher. So I'll put a check every time the experiment was higher than the control. Now by chance, you would think if there was no difference, sometimes the experiment would be higher and sometimes it would be lower. So if the experiment always turns out to be higher, regardless of the numerical value, then something seems to be going on here. It would be like flipping a coin, 16 times, if I do this 16 times, and getting 16 heads. And every time I bet $1 that it's going to come out tails. Now after losing 16 times, I might be suspicious that maybe this coin has got 2 heads on it. Okay, it's like there's something is up. So the null hypothesis is that everything is okay, and if it comes up 16 times heads, then maybe I should start to reject the null hypothesis, and there's something funny going on here. Okay, so that's the basis of this test. So we can ask, what is the possibility for n trials that we have k hits or k successes, given there's a certain probability of getting a success? And this probability distribution is the binomial distribution, which is given by this, nk. This is the number of combinations of n things taken k at a time, times p to the k times 1 minus p to the k, where this symbol n of k equals n factorial divided by k factorial n minus k factorial. Where factorial means we keep multiplying the number times 1 minus the number times 1 minus that until we get down to 1. So 5 factorial is 5 times 3 times 2 times 1 times, it's bad when I can't count backwards by ones, 5 times 4 times 3 times 2 times 1. In factorials are also defined in gamma functions, so we can actually define 5.5 factorial, which you can't do this way. So in the simplest case, to go back to the simplest case, let's say that we run the experiment 16 times, and all 16 times the experimental values are greater than the control. And we don't care how much. They're just greater. Then the probability that this will happen is 2 to the minus 16th. And that's statistically significant. That's approximately 1.5 times 10 to the minus 5th, or 0.00015. 1, 2, 3, right. So that's pretty significant. Now, if, let's say, 3 out of 16 times the experiment was greater than the control, what we'd have to do is do the sum of the first 3 terms in the binomial distribution. So the first term, the probability of getting no successes, turns out to be 1/2 to the 16th. The probability of getting 1 success is 16 factorial over 1 factorial over 15 factorial over 2 to the minus 16th. And that's equal to 16 times 2 to the minus 16th. And the second term is equal to 16 factorial over 2 factorial over 14 factorial, which is equal to 16 times 15 over 2, which is 120 times 2 to the minus 16th. And we keep doing this for the next term. P3 turns out to be 560 times 2 to the minus 16th. So we sum all of these 4 things, because this is the probability of getting none, 1, 2, and 3. And we got 3, so what's the probability of getting 3 or more? And that works out to 0.0106. So in this case, it's still statistically significant at the 0.05 level, although not at the 0.01 level. And again, this was a one-tailed test. If we wanted a two-tailed test, we'd have to double this. So we can accumulate all these probabilities, and they're also in there are tables of these in table A2 in the recommended book, Hollander and Wolf has appendices of tables. We're not so much into tables now because you can compute these on a computer relatively straightforward, but in the old days people were more into tables, and so you can also look this up on a table. So in this non-parametric test, we see how many times the experiment was different than the control, but we don't care how much it was different. Okay, and so this is what's called a binomial test. Now, are there any questions about this? I did this fast in terms of the binomial distribution, but this is described in Spiegel's book. Now, what I'd like to do, in a way, what I've been discussing here is really a paired test. That is, we have a control and an experiment that's the same subject in each line. So we do something to Fred here and Fred there, and do something to Larry here and Larry there, and something to Edna here and Edna there. And we're comparing the two different conditions. So as long as no one turns to dust at that point, the fact that it rings is not significant. These are paired where we're doing two different conditions. For example, this might be 0 alcohol and 1 ounce of alcohol, and we're testing motor ability. So we're comparing one to the other. And so for what we had in the binomial test is we just asked which was greater. So maybe it's greater for Fred and not greater for Larry, but greater for Edna. So this would be 2 out of 3, or 1 out of 3, depending on which way we want to analyze the tail. Another test, which is similar to this, is called the sign test. And it's really exactly the same test. And this is described in Spiegel's book on page 372, and is also no. So let me give a more specific example of this in how we analyze this, because it's really the same binomial distribution. So in the sign test, let's say we had the experimental and control numbers were like this, 10 and 18, 18 and 25. So this is the experiment, and this is the control in the experiment. In this case, the experiment is always bigger. It's always a plus sign. So what we're analyzing is this is really exactly the same test that we did before. And the reason why I'm doing the same thing twice is the test we had before used to be different, but I changed it in real time in my notes to try to make it clearer, and I just changed it to be the one that followed. So that's why we've run into this. And this shows that if I could read ahead at the same time I was reading something in front of me, then things like this wouldn't happen. But so this is exactly the same test, and we can look up the probabilities for this test. And in this case, it's 2 to the minus 4, which is 0.06, that we would get these 4 things in a row. This is almost statistically significant. You can begin to see that these tests are have more what's called power in them than the other tests, the Gaussian test, because even if these differences are small, if we see them consistently, we're going to get a statistically significant result. And so that's why these tests work. Now, in all of these statistical tests, these non-parametric tests, there are going to be 2 ways to calculate the probabilities. So how do we calculate the probabilities for these non-parametric tests? One way is the right way. And you can imagine what the second way is, which is the wrong way. But it's not completely wrong. What? Not so right way. Not so right. Okay, that's good. All right, the right way involves typical things like sums of probabilities. We'll see some of these tests can only be calculated iteratively. Now, this is popular now these days because we have computers and it's easy to do. But in the old days, this was hard to compute. And so what people used to do is compute it once and then sell it. So there were tables. And that's why Hollander and Wolf has all these tables. And I don't like to look things up in tables because you have to take the book down off the shelf and you have to figure out what's in the table. So I'm not into that. So actually, several of these tests I programmed, of course, in BASIC, so I could punch numbers into the keyboard and have the p-values drop out automatically. So I type, and then p's come out. So I computed these. But these, again, have a different flavor. Some of these are actually a little bit difficult to compute. And again, this is more discrete mathematics than calculus, and there are different tricks, and how you set up to do this has to be iteratively. And some of these programs are not so straightforward to do, actually. So that's why people use tables. Now, the other thing that people did is they used asymptotic forms. No, there's no way I'm going to spell this right. But asymptotic forms, meaning if it was Gaussian, from the forms of these things, you can get the formula. Now remember, the whole reason why we're doing these tests is because we assume they're not Gaussian, right? That's the reason why we're doing these tests. So it's kind of stupid to use these formulas, but I found at least some programs use these formulas instead of doing the programming to get the correct values because the formulas are much simpler. And they have a different flavor. You just put them in a fixed way, and sometimes to get the correct values, you have to iterate. You start with a value, and the program keeps crunching and putting those into subsequent formulas to get the value. And it's not written as a fixed equation. And so people don't like to do that. And so I've actually gotten programs that I can tell because I can calculate what the asymptotic value are, and I can see they've given me the wrong p-value. Now, one of these programs on the Macintosh gave a warning something might be wrong. The other one didn't give a warning. It just gave the wrong p-value and cost $300, and the updates were like $150, so I didn't buy the updates and didn't like the program. But it's not so uncommon for programs to do this. In terms of the specific test that we're looking at, the binomial test right now, all of these tests have an equivalent z in terms of the other parameters. So if we have k successes and n numbers, then the z is equal to this formula. And then we calculate the probability from a normal distribution of finding this z. So let's look at this. This is k successes. N over 2 would be the mean. That is, we expect half the times to get successes, assuming a probability of a half. That is, half the time we expect the control to be bigger, and half the time we expect the experiment to be bigger. So the expected value is 50-50. So the difference between the successes, how many times one was bigger than the other, and the standard deviation for a Gaussian is the square root of npq, where n is n, p is the probability that's a half, and q is 1 minus that probability. And so that's why we get n over 4 here. Now, why this is just sigma and not the standard error of the mean underneath here in this asymptotic form, I don't know. So this seems to have the wrong form to me. So I can't explain that. But so if we do a binomial test and we don't want to do that much more complicated expression, and remember, it is more complicated. Remember, I wrote down all this stuff before, right? And you have these factorials, and you have to cancel it out, and you have to multiply it with 2 to the minus 16. We can approximate adding these three things together by this binomial. And in this case, did I do it and get the value? I'm trying to see if I did it here and got the value. 6, 5 minus 3 equals 1.63. It looks like I got the z value, but not the p value. It looks like the z value here was 1.633, but I don't have the p value. So we should be able to look up the p value here for 1.6, one-tailed. So let's see if I can actually do these things now. So 1.6 would be 0.015, right? In order to make this 5. Is that right? No. Well, let's see. 0.63 is 0.4452. So let's start with that. It's 0.4452 subtracted from 5. It shows I'm getting tired. This is 8, 4, all right, 5, 0. So the one-tailed p-value here would be 0.05, and the value we got from the binomial test was 0.06 in this case. Okay, so in this case, they're not too different. This was the value calculated from the asymptotic formula, and this is the value calculated exactly. It's beginning to look sort of ugly here in the corner, but this shows that the asymptotic formula that I have given you up here is not so bad compared to computing things exactly. And that the formula works, and even when I'm tired, I can look things up in tables, but probably not interpolate correctly in tables. Why don't we, so we've done the binomial test. Why don't we take, before we take a break, we have to do one other thing with this test. That is, if we have the experiment and these control numbers, one of the things we would like to do is we now know that, let's say we did this 16 times, we now know that H naught is false, that the idea that both of these are the same is not true. But we would like to get an estimate of what the difference is. That seems reasonable, right? Now, in the other tests, we would sort of have that because we compare the means. And we haven't done that yet here, right? We haven't looked at the mean of one compared to the mean of another. So one of the things we would like to do is to compare, to get a good estimator of what the mean are. And I'm going to show you one way to do that. One way to one way we could do is like we could do the means, but we don't want to do that because if each one of these is a little bit bigger than that, but there's a big spread here, the means here may not be a good estimate of what the differences are. So one way would be to make a table of the differences here, which in this case is 1, 3, and 1. Did I do that right? Thank you. And what we can then take is the median of these differences. So I've defined these differences zi, not equal to the other z, as xi minus yi. That is, let me call it delta I equals experiment minus control. And I take the median, that is the number of which is in between in size, and that's a good estimate of the difference. And we haven't used any means here, so we haven't used any parametric statistics. And this is a good way to estimate the amount by which these things are different. The way we do the median, remember, we look at all these differences. In this case, there's only 3. We order them, and we take the one in the middle. Excuse me? No, we would, thank you. In this case, we would keep the signs. Okay, so if there were minus signs, we would keep a minus sign. Now, taking the median is a little trickier than this because how we handle ties is sort of a problem. And if we have an even number of things, there's none in the middle. Typically, if you have an even number, you may take the 2 middle and average them. That might be a way. So there are a number of more subtle things that go on here in taking the median. As I said, in handling ties is a little bit of a problem. This is discussed in Hollander and Wolf. In the programs that I write, I don't worry about it, so I don't handle ties. And I usually do handle the even things. If it's even, I usually take the 2 middle ones and take the average of them. But it's not usually a big difference. So we'll continue around 10:30.